This is example 5-2, flow over a bump. So basically the situation that we have a rectangular channel. It's flowing from left to right. And we've installed a small bump in it. So we can use that bump, the flow of this bump, right? It's going to move faster. So the whole thing is going to contract a little bit, and we can measure how deep that kind of dip is here at B. And based on that, we can figure out what the flow in the channel is. And so what we'll do, first of all, of course, we have to figure out, can we use our Bernoulli equation? What do we have to have, right? It's water, so it's an ideal fluid. So inviscid and incompressible is comprehensible but not compressible. We have steady flow. It doesn't say anything about changing over time. And then we can say, if we look at a point right up there and one right here, then we can say they're on the same streamline, right? We have the streamline that goes like along the surface like that, so we can say same streamline. That means we can write our Bernoulli equation. We can say PA over gamma. Here we can just leave it all as water, plus the velocity at A squared times 2g plus ZA should be the same as PB over gamma plus VB squared over 2g plus ZB. And now we just have to go through and figure out what all these are. We are, of course, in the end interested in what either VA or VB are, because if we have that and we're assuming that the flow is uniform over the cross section, right, then we can get the flow rate, which is what we want to get. But maybe we can start with the two pressures, right? We know that PA and PB, or the points A and B, are at the surface. So we can say A and B in contact with the atmosphere. So that means that PA and PB are equal to 0 because we're looking at gauge pressure. Then let's put the datum. So we'll put the datum at the bottom of the channel. Datum at the bottom of the channel. So that means for ZA, that's of course just going to be 1.5, right? If this is where my datum is. So it'll be 1.5 meters. And then ZB is going to be what? Well, it says 1.5 from the top of the bump to the water surface. So we have to add 75 millimeters to that. So we'd have 1.25 meters. And then plus 7 millimeters, so 75 millimeters meters, for a total of 1325 meters. All right, so now what do we have? We have PA, we don't know VA, but we have ZA. PB we have, VB we don't have, and ZB we have. All right. Let's write that down. All right, so we'll have 0 plus VA squared over 2G plus ZA is equal to 0 plus VB squared over 2G plus ZB. So now that means we have one equation and two unknowns. So that's kind of a little tricky. So what else can we figure out? Well, we can also use our continuity equation without going through all the steps again. But right, we know that the flow across this cross section has to be the same as the flow across that cross section, because there's no inflows or outflows, and it's an incompressible fluid, so there's not going to be any changes in volume. So we know that, or there's no changes in density. I'm sorry. So we know that happens, right? That we can just do the continuity equation. So what can we say? Maybe real quick, right? We would know this is our control volume, right? We'd have an A in this direction, an A in this direction, and then a V in this direction and a V in that direction, right? So we know at A it's going to be negative because they're in opposite directions, and then B it's going to be positive. Switch back to blue, right? So we can say from continuity equation, we get minus VA times AA plus VB times AB is equal to 0. All right, so what can we learn from that? Well, we can learn from that of course we can solve it for one of the two velocities. Here, let's do VA. So VA is just going to be VAB, the area, B over the area at A times the velocity at B. All right, so now it's our cross section. Our cross section now is not, most of them were circular, right? But now it is a rectangle. We know that at, what do we need first? We need B first, right? At B it's going to be 1.25, and it says it's 1.5 in width. So we'd have 1.5 for the width times 1.25 for the height, divided by 1.5 for the width. And now here, this one, of course, we have the depth of 1.5, so times 1.5. So the first 1.5s cancel out. Oop, let's not forget, this is all times VB. So based on that, we can say we get 5/6 times VB. All right, so now we know we have a relationship between VA and VB. Yep, where's our equation right here? We can plug that in there, and then we can solve either, or in this case, we solved for VA, so we'll solve this one for VB, and then we can get our flow rate. So based on what we have here, right, so we said VA squared over 2G, so now we have our VA, so it'd be 5/6 VB squared over 2G, plus, we'll leave ZA in here for now. Change that later. ZA is equal to VB squared over 2G plus ZB. All right, so what else can we form from that, right? So we can solve that to get the VBs on one side. So if we do that, then what do we get? We get on the, if we leave ZA over here, so we'd have ZA minus ZB. If we bring ZB over, that means we have VB squared over 2G minus, I guess that would be 25 over 36 VB squared over 2G. That means we can pull that out, the VB over 2G, right? So we'd have that's equal to VB squared over 2G times 1 minus 25 over 36. Right, that's what's left from that. And then we can say, well, that would be 36 over 36 minus 25 would be 11 over 36. So we have 11 over 36 times VB squared over 2G. So we get 11 times VB squared over now 72 times G. All right, I think that's all we need. Oh no, we still need to divide this through with our z's, right? So if we bring this to the other side, we want to just have VB, right? Then we'd have VB would be then, what do we have? We had ZB on this one side, so we'd have ZA minus ZB times 72 times G, and then all of it is divided by 11. All right, very good, right? That's makes sense to us right now because the only information that we need, it's only the information that we have, is how basically this water level changes at point B. Right? And that's the only thing we have. ZA minus ZB, right, would just be kind of this dip in the water level as it flows over this bump. Right? Again, we get this bump because the water is flowing faster over this bump than before and after. All right, we're not asked for the velocity, we're asked for the flow rate. So to do that, we just have to say Q is equal to VB times AB. VB we have up there. Maybe we'll do, so it'll be ZA minus ZB times 72 times G over 11. That's our velocity. And then times the area. Now we're at B. Let's see, B is here, so it's 1.25 times 1.5 meters. And then we can plug all those other values in. So again, square root of, at A we said is 1.5 meters, at B we said 1.325 meters, so that's good, that's positive. We want to get a positive number at the end. 72. G, of course, 9.81 meters per second squared. All this divided by 11. And then times those two. 1.25 meters, 1.5 meters. And then if I plug those into my calculator, I get 6.28528 meters cubed per second, or if we round it, this is a 5, but 8 is even, so it doesn't change. 6.28 cubic meters per second. Right, so this is, now we figured out what the flow rate is. So this approach is actually quite common if we're trying to figure out what the, if we have some kind of a channel that has water flowing through it and we want to know, over and over what the flow rate is, right? Then we can just put a little sensor up here, a little eye that's looking downward that measures what the water level is here and what the water level is over here as well, right? And then just based on those two measurements, we can easily figure out what the flow rate in this channel is, right? So we could have a little computer program that just continuously tells us what the flow rate is. And if we needed to, we could, maybe we have some control up here where we can make the water flow, more or less if we need to.